Hello, and welcome to Fun with Zircon. I have been working with zircon megacrysts from the Isle of Iona with the hope of answering the following questions. What are the age of my samples and their surroundings? Do they record any metamorphic events? What's the petrogenesis of this zircon population? And if they are primary grains, where did their parent fluid or melt come from? My samples are from part of the Lewisian Gneiss Complex, a suite of highly deformed polymetamorphic Archean rocks, of which Iona is the southernmost outcrop. The para-amphibolite group of Iona, here denoted PA, has yet to be dated. This could be the key to understanding Iona's place within the complex. My field site comprises amphibolite facies metabasic rocks, punctuated by igneous intrusions of differing age. One of the oldest of these intrusions is the pegmatite vein at my feet. Composed primarily of sericitised feldspar, it has quite a complex interaction with its hornblende pyroxenite host. And this is where the zircons come in. Zircon, or zirconium silicate, typically forms crystals between 20 and 250 microns long. It's most commonly found in silica-rich rocks, so if you were to ask any geologist to find zircon in this image, the most obvious choice would be the pegmatite. Now, amongst zircon's many useful properties, it happens to be photoluminescent, so I took a UV lamp with a wavelength of 254 nanometers into the field to help with my investigation. Not quite what you would expect, is it? The zircon crystals are concentrated in the pyroxene amphibolite, suggesting a fairly unusual metasomatic origin. Zircon is also cathodoluminescent. When bombarded with electrons in a scanning electron microscope, it emits electromagnetic radiation. Intensity of luminescence varies with chemical composition, allowing us to see growth zoning within the crystals. Each zone here may tell us about fluctuations of available ions in the parent melt or fluid as the mineral was forming. Zircon has become an indispensable tool for geochronological and geochemical studies of rocks. By using laser ablation mass spectrometry to date zones and analyse trace elements within these samples, I'm hoping that this population, taken from within the pegmatite and host rock boundary, can give us the information needed to start answering my opening questions. The size of these grains allows for ablation of multiple areas from the same zone, allowing us to build a picture of melt fluid composition through time. That brings us to the end of this episode. Thanks for watching, and tune in next time for results and interpretations.